apart from using HBr, HI, or HCl to convert an alcohol into an alkyl halide, we can also use PBr3, phosphorus tribromide, phosphorus trichloride, or thionyl chloride to give the respective alkyl halide. In all of these cases, we are going to use pyridine. Pyridine is going to act as a base and as well as a solvent. Let us now look into the mechanism for the reaction with PBr3 or PCl3. They are going to follow exactly the same mechanism. First, the alcohol, the OH group with its lone pair of electrons, is going to go and attack the electropositive phosphorus, and one of the bromines is going to leave. Okay, let's draw the structure of the intermediate that's obtained. Remember, the hydrogen is still intact. Okay, and one of the bromines has already left. Okay, so here is going to be the structure of the intermediate. Now, your pyridine, which is a solvent and also as the base, is going to act as a scavenger to abstract this hydrogen. And it's going to neutralize this positive charge on oxygen, thereby making this into a good leaving group. Now this part right here is going to be a good leaving group. Now in the next part, the Br minus, which is going to be a nucleophile, will go and attack this carbon in the side that's opposite to that of the leaving group, and the leaving group is going to leave. And this is going to be your SN2 reaction, right? And there you have your final alkyl halide. And if you want to write the mechanism for with PCl3, it's going to be exactly the same. Here you will be replacing the bromines with Cl, and you will be getting the alkyl chloride, ethyl chloride. The mechanism for the reaction with the thionyl chloride is pretty much similar. Let's look into the mechanism for it. Here again, the electrons from the oxygen, the lone pair of electrons from the oxygen, is going to go attack the electropositive sulfur, and it's going to thrust one of the chlorines out. Let's write the product here. Again, the hydrogen is intact. Now the pyridine comes into action where the hydrogen will be abstracted by pyridine, and it's going to neutralize the charge on oxygen. Now you have an intermediate which is going to be present with a good leaving group. Here is your leaving group. Now the Cl minus is going to come in a direction that's opposite to the leaving group, and the leaving group is going to leave. And finally, you will be getting your alkyl chloride. Okay, so this is called as the chlorosulfide group. Chlorosulfide group. And in the previous example where we had the reaction with PBr3 or PCl3, we'll be forming the bromophosphide or chlorophosphide group. This is going to be a good leaving group. Now, in all these reactions, we have seen an alcohol can be efficiently converted into an alkyl halide. An alcohol can be reacted with either HI, HBr, or HCl. We need to make sure that we heat the reaction, or else the reaction is not going to go. Only then it's going to be activated to form the corresponding alkyl halides. But in the case of HCl, we need to add a catalyst, zinc chloride, to hasten the reaction, to make the reaction go fast, because it's super slow, because the Cl minus is a poor nucleophile. And also, the second way to activate the alcohols is using either PBr3, PCl3, or thionyl chloride. The next way to convert an alcohol into something useful is going to be converting that into sulfonate esters. Primary and secondary alcohols can be activated by being converted into sulfonate esters. For the formation of sulfonate esters, you will take sulfonyl chloride. Here is the general formula for sulfonyl chloride. And here are the most common sulfonyl chlorides, depending upon what the R dash is. So if the R dash is a toluene group, then you're going to call this as toluene sulfonyl chloride. This is toluene sulfonyl chloride. and it's abbreviated as TSCl. And if the R group is a methyl group, then it's going to be methane sulfonyl chloride. Methane sulfonyl chloride. And if you have a trifluoromethane group, this is the trifluoromethane groups where the 3 hydrogens are replaced by fluorine. Therefore, it's a trifluoromethane sulfonyl chloride. Or you can also call this as triflyl chloride. This is called as tosyl chloride. And this is called as mesyl chloride. And it's abbreviated as MSCl. Okay, with each one of these, the sulfonate ester is formed. Okay, let's look into the structure for the sulfonate ester that's formed. In all of these reactions, we are going to use pyridine. Again, pyridine is going to act as a solvent, and also it is going to act as a base. Okay, now the product that's going to be formed here is going to be a sulfonate ester, which is going to have this structure. Okay, so this does look like an ester, right? So it's a sulfonate ester. Apart from that, you also have the protonated pyridine, and also your Cl minus. Okay, one important thing to say about the sulfonic acid is a very strong acid. It has a pKa value of about -6.5, which means it's definitely a very strong acid. And because it's a strong acid, we can definitely think that the corresponding or the conjugate base is going to be weak. Now, why it should be weak? If I'm going to pull the hydrogen here, that's definitely going to put the negative charge on this oxygen. But this negative charge is not going to exist on this one oxygen. It is going to be distributed between all of these 3 oxygens, because of which you have 3 resonance contributors, and therefore it is going to be stable. And because it's going to be a stable base, it's going to be a good leaving group. Remember, a weak base is going to be a good leaving group. Let's look into the mechanism for this reaction. Okay, first thing is an alcohol is actually going to react with the sulfonyl chloride. Okay, and remember, you can use any of these sulfonyl chlorides based on what the R is. Okay, in the first step, the lone pairs of electrons from oxygen is going to go attack the sulfur, and it's going to thrust the chlorine out. Okay. And remember, you still have the hydrogen on it, and this oxygen is going to be positive. And this reaction doesn't happen without pyridine. So the role of pyridine is going to be both solvent, and also it is going to act as a scavenger, basically as a base, which is going to go grab the hydrogen. So it's going to go grab this hydrogen and neutralize this charge. Now you have your sulfonate ester. So this sulfonate ester is going to be a good leaving group. And therefore, you can react it with any nucleophiles. Nucleophiles such as Cn- or nucleophiles such as CH3S-. All of these can react with the sulfonate esters and form the corresponding products. Let's write down the products for this reaction. Your S- is going to be a nucleophile. Remember, this reaction only happens with primary and secondary alcohols, and therefore you are going to get primary and secondary sulfonate esters, right? Remember, the SN2 reaction does not happen with tertiary alkyl halides or tertiary compounds, right? So the nucleophile will go and attack this carbon from the side that's opposite to the leaving group, and the leaving group is going to leave. Okay, let's write down the products. This is one of your products, and the other product is going to be a tosylate ion, which is going to look like this. And remember, we said that this is a good leaving group. Why? Because whenever it leaves, these electrons are actually going to be distributed between 3 oxygens, and therefore it should be a weak base, stable base. And in the same way, the cyanide ion can go attack this carbon, and the leaving group is going to leave, and in which case you're going to form a nitrile. The product here is going to be this and your tosylate ion. So we call this as tosylate ion because it has an oxygen with a negative charge on it.